So I have a coin. If it's unbiased, the chance of having head or tail is 50-50. Right? So coin toss, unbiased, tail is 50%, head is 50%. If it's biased, I may have some probability for heads P, and this is 1 minus P. Suppose I have a coin, I want to see if the coin is biased or not, right? What would you do? You would throw the coin in the air, see what happens. Can you tell if it's biased from one trial? The coin tosses in the air, you see the result, it's a head, right? Toss it again, it's another result. Say that's a tail. Toss it again, it's a head, tail, and so on and so forth. If you run enough tests, at some point you can estimate this speed, right? I think we mentioned this before. This estimate has a certain variance and so on and so forth. So that's called statistical estimation, right? If I throw a coin in the air 100 times, I get an estimate for the bias of the coin. And depending on how many times the number of trials, which is the number of tosses, say that's n, and h is the number of trials that have heads as result. So the estimate, not smoother, is h divided by n, right? Take how many heads I've seen divided by the number of trials. That's the estimate. My point in here is not about this estimate. My point is n has an implication for confidence. That is, I could get the same estimate by tossing a coin 10 times, or 100 times, or 1,000 times, or 1,000,000 times. I can get the same exact P 0.6. The point is the n, the bigger the n is, the more confident I am in my estimate, which is the same as saying the confidence intervals, right? Interval. Let's call it 95% confidence. It's pretty standard to say when you want to be sure of something in statistics. There's never sure as in perfectly sure, but people say about it's a 95% chance to be correct. 95% confidence interval, it's something that you could say, hey, my estimate is here. This is P estimate. And this is the interval, right? This is the confidence interval. Meaning it could be from here to here. Like the actual estimate is 0.62, and it could be up to 0.67 and below to 0.57. Now what's going to happen with this confidence interval? This is why I'm 95% sure that my estimate is this value. The question is, where is the actual P? Right? So this is the true P confidence interval. I'm saying if my estimate, P estimate is here by flipping the coin, 95% of the time, the real P will be between this and that. That's my confidence. So now, what's happening if I increase the n? I do more trials. P estimate varies a little bit maybe, but it's roughly the same, 62%. What's going to happen with this 95% interval? I'll become more sure. More sure means what? It shrinks, right? Instead of having a plus minus 0.05, 95% confidence, I'll keep my confidence at 95%. I'm allowing myself to be wrong 5% of the time. So what's going to happen, instead of this, I'll get, so this is say n equal, I don't know, 20. I'm guessing there, and here's n equal 2,000 more trials. My P estimate is roughly the same. But what's happened to the confidence interval is much smaller. 95% of the time, I'll be very close my estimate. I know that because I flipped the coin so much more many times. Okay, so that's how statistics of estimation goes. Now, we want to kind of maybe flip this mechanism to its head a little bit and say, what we want to test is a hypothesis. Right? So now we're asking, is the coin biased or not biased? Let's say not biased means around 50% heads to tail. Right? I mean, it could be 50 and a little bit. So this should be an easier question, right? One thing is to estimate the bias exact, to say what is the bias, 62, 75, 51, 50. And the other question is to say, is it biased or unbiased? Right? I'm not asking how much bias it is. I don't want the 62. I'm just saying, is this a 50-50 coin? Right? Or roughly 50-50. We can't measure, there's no way to measure a coin that's 50.0001 biased to fit on, on its head. I mean, there is. The statistical number of trials we need to do to verify that coin will be in the hundreds of billions of trials. Because the bias is so small that to notice and to be confident that there's a small bias, you need a large number of trials. So I need you guys to understand first the principle. In statistics, when we measure some sort of generative bias, this is an inherent bias of a coin. The part with the tail, it's a little bit more heavy by construction. You know, somehow the alloy got a little bit more heavy on that chance, right, on that side. So it has a heavier chance, bigger chance to go on the tail side, for example. Right? If that's the case, the difference is very small. To measure small differences will take a lot of trials. To measure big differences, that's very easy, right? So that's the same challenge that happens in a lot of places. If you are a recruiter, you do interviews, right? You're going to distinguish immediately a good candidate from a bad candidate. Like people, one is a superstar and the other one doesn't know anything. That's easy. But when people are really close, it takes a lot more interviewing and tests to distinguish them, to say, you know, I'm going to hire that person. Right? It may not even matter. It may be that they're close. Either one of them hired is probably, you know, the same thing. So small differences are harder to measure, requires more trials. Big differences are easier to measure. They come out right away. So now what we want to do in this statistic for information retrieval, significant testing, is to answer, is this 50-50 chance? We're going to call that null hypothesis. So null hypothesis, it's usually no change or normal, or same. I mean, it's up to us to define what null hypothesis means, but that's the usual stuff, so to speak. So when we're gonna have a conclusion of some kind with those IR metrics that we've been doing last week, we're gonna say, we measure some result. We want to know if this result is due to chance or there is an actual bias. So I'm gonna, before I go to systems in information retrieval, I'm gonna keep talking about this coin for a little bit further. So instead of saying, I want to estimate the P, the bias of the coin by doing trials, I'm gonna flip this question and say, suppose I did the trials. I did n equal 100 trials, right? I have an observation, the number of tails is 45, the number of heads is 55. Right? So what do I notice? This is not exactly 50-50 by observation. But what's the question I really want to ask now? I'm not trying to estimate the bias of this coin directly. I mean, I could, 55 by 100. What I'm trying to estimate is can I declare this coin biased or not? So how do I put that into mathematical statistics? What's the question I need to ask? To say, normally if we look at this bias and do the estimate, we will have what? 55 by 100, right? P. That's what we estimate. So what we want to ask is the question, if null hypothesis, let's call this, I'm just calling it null H. So let's say if null H, what is the probability? I don't want to say probability, let's say chance in English. The chance. Null hypothesis in here means fair coin or unbiased. What is the chance to observe this t equal 45 and h equal 55? In other words, what is the chance that this particular number of heads and tails observed? I already flipped the coin. I have all the results, 100 results, right? In a coin, the order doesn't matter. So I'm just going to keep the counts, 55 and 45. Doesn't matter which heads came before which tails. I'm asking, if this was a fair coin, let's assume hypothesis, not hypothesis, this was a fair coin, 50-50. What is the chance that the 50-50 coin will produce that result? This is a slightly different question than estimating the P. It's saying the coin is fair. Let's assume it's fair. What's the chance that the regular fair coin, null hypothesis means regular coin, would produce such a result? Why would I ask such a question? Suppose I get that chance completely, right? What would I do with that value, probability, chance? This is, I have a fair coin. I know there's a chance to produce that, right? By the way, do you guys know what that probability is? If I have a 50-50 coin, what's the chance to observe 45 tails and 55 heads? How do I do that? So that's a different question. But assuming I have this probability, right? Probability of t equal 40, let's just say heads equal 55, n equal 100, because that's effectively the same thing. Out of 100 trials, I've seen 55 heads. Suppose I can put this probability, right? Let's call it V. What do I do with it? I have this V in my hand. It's a probability, it's a number, right? 0.12 or 0.17 or 0.001, something. What would I do with it? How? Like, not the technicalities. I'm saying, is this value, if it's big, it means what? If this value is big, null hypothesis was wrong, or what? Right.
I mean, it's not exactly.
So that's the principle we need to understand before we get into technical details. If I observe some outcome, in this case flipping 100 trials, I look at, make an assumption, my coin was fair, not hypothesis. Under that assumption, what's the chance to have observed this thing? Now, if that value is too low, it means what?
This is one of
This is what?
this is like one of the random things. The value is more than you're saying that out of 100, the number of times I get 45 days. So many.
So how do we think about this? Again, if the value cannot be too high. I mean, if it's high, it's fine, right? The only problem is when the probability of observation is too low. Right? So I'm going to say here, if V is too low, not defining what too low means. Too low. It means what? I cannot deny my observations. I had the coin and I flip it 100 times. Why V would be too low? Or you can say not too low, but lower. Let me translate that in English. Too low, let's say in English, much lower than expected. Under null hypothesis, right? So as making that assumption with a null hypothesis, I have some expectation for this probability. Okay? And if that's not the case, then
Then the hypothesis is
I do the what? Say again.
wrong. Null hypothesis is not right.
Right. So that means reject the null hypothesis. That's kind of the main. You can't do much with the statistical test. It doesn't work backwards. If it's too high, it doesn't mean you verify the null hypothesis. Usually, for most tests, if the value you get is too low, it means something was wrong with your assumption, and the assumption is the null hypothesis. Again, in our case, the null hypothesis, the coin is unbiased fair. So the reason I got something that doesn't match my assumption is because my assumption is wrong. The coin is not fair. Now let's verify that we've got this exact. So there's two values, right? I think we may have gotten this part wrong, but there's two values. This is the probability so this is the probability to observe this outcome, right? And how do I know what too low means? Like those probabilities could be very low. How do I know that that one is too low, whatever I get?
There's something called Eval, 0.05. If it is less than 0.05 means you can reject another hypothesis.
So V too low, it means V, may I add here another dot. V has to be smaller than a threshold. Right? Data is a threshold from a table. This is not, there's a published table. How V should be, how much lower V should be than the threshold to declare rejection, right? But that table depends on what? It depends on the modeling of the coin, right? The coin that has the null hypothesis has a certain assumption of a distribution of values. Do you guys know how the coin's flips are generated? With every coin, doesn't matter bias and unbiased, that distribution of flips, it's called multinomial, yeah, binomial. It's binomial for one flip, but it's multinomial for many flips. Right? So I'm looking for a multinomial distribution. And in there, I'm checking my value against a published value that's computed, it's pre-calculated. And if it's smaller than that, I'm going to say reject the null hypothesis. The chance of my coin being fair and getting this observation is too small. Now, is there still a chance for that to happen by chance? Any coin can produce this outcome, right? No coin is 100% one way, say head biased. So every coin, biased or unbiased, can produce any outcome out of 100 flips. Agree? It's just some of them are very unlikely to produce that outcome. So if a coin has say 100, high probability on the heads, like 90% probability on the heads, this would be extremely unlikely. This is too close to being balanced for a coin that has 90 or 99% of the heads, right? If I have a 99% probability of the heads, once I flip it once, there is still a chance to get a tail. That's 1%. But to flip it 100 times and get 45 tails, that's almost impossible. So to recap this process, we start with the hypothesis. The null hypothesis doesn't have to be balanced. It's whatever you think is normal. Maybe for me, normal is I'm a factory, I'm manufacturing biased coins. That's what I do, biased coins. So I have different matrices for manufacturing those matrices, depending what the customer wants. That's my bias I implement in the coin. A customer comes to me and says, I want a 70% bias coin towards heads. Fine. So I try to make 70% biased. I put the price at 70% biased. But then when I measure the outcome of those coins, I'm asking, what's the chance that a 70%, that's my null hypothesis now, because that's what I expect to get, a 70% biased coin. My fee is 70%. Then I'm asking, suppose I throw that coin 100 times, and I get 55 heads and n equal 100 trials, so 45 tails. I'm asking, what's the chance with a 70% biased coin to get that result? And if that's too small, it means my press didn't work properly. It didn't produce 70% biased coin. Of course, if I have, this probability will increase if the true bias of the coin is close to 55%, right? The closer the coin is to 55%, what I notice in practice, that would be my estimate, the more I cannot reject, right? In those statistical tests, we never accept. We say we either reject the hypothesis I started with, or we don't know. So the basics of a test are a model assumption, an experiment, let's say trials, some statistics observed. This is how many heads I've seen in my experiment. Then a test. This is the null hypothesis here. A test that compares this is the V, the statistics. Sorry, this is not the V, this is the 55 by 100. Test that says, what is the chance under the null hypothesis to observe these statistics? Let's call it this V value. And then we have two options here. Either not reject or reject. That is, we're not going to be sure that the null hypothesis is correct. That's not the outcome of a test. The test doesn't say you were correct. The test is going to say you were wrong or I'm not sure. So a little bit more detail about mathematically how this stuff works. What we want to do from a model is to look at, let's say, draw a simple model of a Gaussian distribution. What we want to say is the value that I'm expecting is here. This is a nice model Gaussian. Most of the experiments, even with a coin, does not follow Gaussian distribution. But this is the expected value. And this is what I've got. This is the value. So the tests usually look at this area here and say, okay, how much probability mass you missed. If this is smaller than 5%, typically it's 95% confidence. If this is smaller than 5%, then you declare certainty or not rejection. And if it's within, the farther this V is from the expected value, the smaller the chance is that my assumption was correct. So that's what we want to do for information retrieval evaluation. What stands typically for the trials? So now making an analogy with the information retrieval systems, what are those trials that allow me to become more confident? So with this coin, if I flip it once, I don't know much, right? I don't know almost anything. If I flip it twice, I know more. If I flip it 3 times, I become more confident, right? So suppose I'm comparing 2 information retrieval systems, right? That's what these trick people do all the time. They have hundreds of systems and they compare them. Or you can compare your BM25 with your JellyMac, or your BM25 version 1 with BM25 version 2 with BM25 version 3 as you keep developing, right? What is the trials? Number of queries, right? So the more queries I run, the more confident I become in my result. So for information retrieval, typically trials means queries. And if I have 2 systems, say A and B, the null hypothesis typically is A and B are roughly equally good. So in terms of performance matrix, the 2 systems are not significantly different. Right? So now if I run many queries and I observe consistently that system A does better than system B, I start to question my null hypothesis here. I'm starting to say, hey, I think there's something wrong with my null hypothesis because this system A always gives me better average precision than system B. There's the small difference, not so small actually, between this and the analogy. When we flip a coin, there is no intermediate result. It's either black or white, right? It's either head or tail. The truth is, when we measure information retrieval system, it's not really for a query better or worse, right? We're not simply asking when we compare system A, Google, with system B, Bing, for a particular query. We don't say Google was better. We have this performance metrics, so we look at the difference. They might be a lot better or little better, right? So we have to take into account the actual difference in the metric that we care about, precision, recall, or F1, or NDCG, or whatever metric we use. It's not black and white. We can't take NDCG and say system A is better if it's just 0.00001 better, right? So the coins for each trial gives you a black and white outcome. For us, it's actually more difficult because we have continuous values to worry about. So let's go to some slides. Is that right? The lamp is gone. Up to this. Well, so we're gonna stick with green then. So there's many reasons, of course, to compare two systems. For example, I implemented stemming, is it better? So I make a change, is it better? I've got this result, I'm comparing with my, other student, is it better? So we have a null hypothesis, we said that. What we want to compute is, I'm not insisting on any math formulas right here. Those are typically the formulas that nobody remembers unless you read in statistics, you do your career in statistics. Everybody will check the formulas to see how they work when you do the test. Yeah, even me, I remember the exact formulas. But you have to remember the principle. When I run something under some assumption, I'm asking, is that probability for what I observed too low? If it's too low, means my assumption was probably wrong. So that's the case when I become sure, aka statistic that means confident, that I can reject things. How do I know system A is better than system B? I start with the assumption that they are roughly equal. I run it over 25 queries or 50 queries or 100 queries, or how many queries do I need? System A performs better than system B consistently. After so many queries, I become more than 95% sure that the null hypothesis is wrong. The null hypothesis meaning the two systems are roughly the same. So then I say, I reject the null hypothesis, I'm at least 95% sure that system A is better. If that doesn't happen, I call it inconclusive. Like this other branch that says not reject. It says, under the null hypothesis that the two systems were roughly equally good, based on the observations I had, the queries I ran, the performance metrics I observed, I cannot reject that hypothesis. There is still a reasonable chance they're equally good, and whatever differences I observed are due to natural chance. So let's say, see one of such tests, right? So there's a target here. I release the precision is at least 75% chance, right? So the precision, I need a precision that's that high. So I run my test, right? How? I run a bunch of queries, right? I estimate an average, and I have a formula here how to compute a t-test in this case. That's a math formula that we need. And then I'm saying if I look into a table, if this value is bigger than something, I say good. If it's more than something, I say I'm not sure. I can't promise you a precision bigger than the number you gave me. So the formulas exact come from understanding the nature of these distributions and certain statistics about them, mean, variance, mode, so on and so forth. So here's an example, right? I've got some values, and I run the test, and I say, okay, the probability I get at the very end. So this number, how does this fraction compare with this, right? Who is 0.764? That's the average I've got, right? The mu is the target divided by S is standard deviation of my values, right? And square root of n, who's n? Number of trials. So I'm running 5 queries here, right? I get this value, 0.73. This is computed from a table, right? So what does this mean? In here. Right. I think. So in here, if I get this 0.23, first of all, what is my null hypothesis here? What's the null hypothesis? So let's see how this works. What's going to happen if I get a very good system, the one that my company wants to release? This X bar will be equal. It will be very high, right? This X bar, if I get a 95% system precision, I get some queries, I'm going to get very good results, right? So this will be 95 minus the mu. So I get a good difference there. And the standard deviation will be very small. If I get all the values high, that's going to be small. So this t will be very high. So the probability that the other t, that's the distributional t, is bigger than my t will be
Small.
very small. So that's when I get a very good system. In here, this t that I'm getting in there, and the probability that is bigger than the mean is too small, right? This is too small to say I'm rejecting the null hypothesis. And the null hypothesis is what? The performance is at most 75%, right? That's the null hypothesis. In order to, if I would get a very low p-value, right, I would say, okay, that null hypothesis doesn't hold, which is what my company wants, to have a reasonable confidence that the system is not below or at most 75%, right? I can't reject it here because this value is just, this is the probability that the X is bigger than the mean. So this is, I want, what is the chance looking at these values to say with confidence that when you run the system, you get more than 75%. This value is not enough. And there are variations of this stuff, like for example, I have two systems, A and B, and I want to know whether one is better than the other. Null hypothesis would be they're the same. What should I do though now? Instead, I don't have a fixed threshold 75%, I just have two systems. What can I do per query? Take the difference between the average precision or the NDCG values or whatever my performance metric is. So I say I do average precision. I'm going to compute the difference between the average precisions, and those are my values now that I feed in. The target in here is what? Before was 75%, but now that I have two systems and I take the difference, the target is 0. So the null hypothesis, once I take the difference, is that these values are reasonably close to 0, or at most 0 if it's one-sided. If I manage to reject this hypothesis, say, no, those differences are not statistically close to 0. They are significantly higher than 0. That means what? The null hypothesis is wrong, meaning the system A, the one that, because this difference is always from A to B, or x1 to x2, right? If I manage to reject this hypothesis that the systems are roughly the same, or A is at most one-sided, means A is not better than B. I take the differences, I run the same test, right? The reason there's no mu here is because the mu, the target, is 0. If I reject this hypothesis, it's going to be like A is not as much as B. It's much bigger, significantly bigger. I know what I'm saying is, if somebody from math department will come to this lecture and say, what, you don't explain these formulas, this is the cool part where this is the square root divided by the variance comes into play. Yeah, mathematically speaking, that's where the interesting part is, right? How do you relate this test with the confidence interval? I think we had it somewhere here. Mathematicians are all about how do you compute confidence intervals giving an assumption like multinomial, binomial, you know, this kind of distributions that you are assuming, how those formulas work out. That's fascinating, but it's not the problem you're going to have if you use significant tests. You're going to look at a table and you're going to look at the formula anyway. The problem you're going to have is to understand what a test does. Okay? So, the formula, some mathematician figured out how a distribution, an assumption distribution, in this is the student t distribution, right? That's how it's called. How that formula, once you have a bunch of observations, gets to derive the confidence interval. And then the effective test that we've been talking about, where we're asking, can I reject or not? Back to the confidence intervals, the first thing we wrote on the board. When can I reject? I got an estimate, right? And I've got something from the model assumption. A fair coin should have what bias? 50. So when do I reject the 50%? I look at my estimate in here is 55, right? The confidence intervals, given the number of trials I did, it says, well, it's 55, but you're really between 47 and 62 or something, right? Because you didn't do enough trials, you have a large margin of error with your estimate. When can I reject the hypothesis? Where is the hypothesis? The value that theoretically I should get if the coin is biased. So this is 55%. Where is the 0.5 in here? Here, right? This, we say this is maybe between 62 and 47. So this is the 50. This is what the null hypothesis says. It should be 50-50. But 50-50 is still within my confidence interval. So it's possible that my estimate, which was 55 from my trials, because I flipped the coin 100 times, I got 100 hits. It's possible within 95% confidence, this is the interval, that 50 is still within 95% chance to get it. So I can reject the null hypothesis here. The coin might still be fair, and there is bigger than 5% chance to see this result. If I run it a lot, this is still, say, the 55.55, but this is between 0.57 and 0.53. It's much tighter now, 95% of the time when you see this big here. Now I can reject the null hypothesis because the null hypothesis is still at 0.5, so I'm saying that's not within 95% chance. There is always a chance to be wrong because any coin can produce this distribution, right? The question is how often you're going to be wrong. In here, we're going to declare rejection, and we're going to be correct many, many times, at least 95% of the time. We're still going to be wrong sometimes, because any coin can produce any particular set of flips. Right? What else do we have? Some some examples how to do pairs. I wanna do one more type of test, not a t-test, which is all based on that formula, either with differences or the values that you get from measuring performance over queries. Some people have thought, here's what we're gonna do. This guy, Wilcoxon. He said, I have two systems and I measure their average precisions. Let's suppose I got these kind of values. This, of course, it's consistent. That's query 1, query 2, query 3, query 4, query 5. I'm comparing apple to apples. This is the values there. What I'm going to do is take the differences like before. So 74 minus 77, minus 0, 0, 3, right? 82 minus 86, 0, 0, 4. 71 minus 74, that is minus 0.3, 0.4, and 79 minus 0.02. That's the same like in the t-test. I take the differences between the metrics that I care about. But then, I sort those differences by absolute values. So I reorder the queries. Like these differences, this is the query 1 difference, query 2 difference, query 3 difference, query 4 difference, query 5 difference. Right? You guys look mystified. So I look at those differences and I reorder the queries in such a way that the smallest differences are at the top, absolute value, because they could go either way, right? So what is the smallest difference?
0.0.
Is 0.03 or 0.04? That's the biggest difference.
Minus.
The guy who wrote this slide is wrong. There's a bug in the slide, I think. Sorry about that. So I think we need to sort by the absolute values. If we sort by the absolute values, the smallest one on the top, that would be 0.02. And that should count as a 1. So the way we count them here is ranks. We replace the actual values with ranks. What I remember is that in this case, 0.02 is first. And then it counts as a 1. 0.03, I think what happened here, they got sorted by backwards. So the highest values were at the top, right? So imagine if I sort by the highest absolute values, what's going to be at the top? 0.04, and the other one will be minus 0.04, right? Because they're the same value, the ranks get distributed. It's like in tournaments where 3 people get the same score. They get rank, all get rank, they get ranks 1, 2, and 3, divide by 3, everybody gets rank 2, sort of thing. That's the same happening here. I think this sorting is incorrect. My recollection of Wilcoxon is that this is sorting by the smallest first. But if I sort it at the highest, I'll get 0.04 at the top, those are the 1.5 and minus 1.5. Then the 0.03s, those are those two values. They both in the same way because they're both negative, right? As opposed to the 0.04, which were one positive, one negative. And this 5 would correspond to 0.02, right? But I think this is incorrect. I think if it would be me, I would sort it the other way. So what ranks would I get if I sort this with the smallest at the top? The first one will be 1 because 0.02 is positive. Then I get the 0.03s. Those get what kind of rank? 2.5 and minus 2.5 because I'm distributing 2 ranks, 2 and 3, 1 plus, 1 minus. How? Oh no, they're the same way. They both negative, right? And the 0.04s would be?
Minus 3.5.
3.5 and minus 3.5?
Yeah.
So I'm kind of betting on this array of signed ranks rather than this. But that's a small difference. And then this Wilcoxon test, which that's what people like about it, is that they sum this up. They say, okay, let's sum up. How much is the sum here? Is it 1?
Okay, no.
This goes away with this.
Yeah. Then it's -4.
Minus 4. How about it here? If I sum it up in here, how do I get it?
-2.
Minus 2. So depending of how big this value is one way or the other, again I have to compare with the threshold like in the other statistical test. I get a sense of how much better one system was. The null hypothesis being here, this sum should be roughly, if the system are equal, what should I get roughly from the sum? 0. Because at equal ranks, I'll get roughly equal differences one way or the other. The reason I'm thinking this is probably correct and not that, let's run into extreme. Let's say system A is losing on some queries by a little bit, but winning on some queries by a lot. The difference into my sorting versus this sorting is that in this sorting, the big differences correspond to what values? Small values, right? The bigger the difference is, the more it goes at the top. So that corresponds to small value. In my system, my way of ranking, if there's a big difference for a query, my system versus his system was a lot better by average precision, 0.5 versus 0.1, a huge difference. That corresponds to a big rank, so that makes a big impact. I think this is correct because small differences correspond to relatively small values, while big differences correspond to big values.
But isn't that small? Like if you x1 minus x2, like it's like almost close.
So when what happens in here, if this is another bug, I think this is x1 minus x2, right? Yes. So when you get a really close to 0 difference, right? In here, the difference itself doesn't matter, right? It's just the order of differences that matter. The difference itself gets mapped to the first difference, second difference, third difference, fourth difference, fifth difference, right? So the smaller the difference gets a smaller rank, and bigger differences get a bigger rank. Which one do we want to matter more in our overall formula? I think the biggest differences is the one that count, right? In other words, suppose my system wins 3 times against his systems by a little bit, but his systems win only 1 time by a lot. So my system gets on 3 queries 0.01, 0.02, 0.03 improvements. And his system gets improvements that are 0.4 and 0.6 over my system, 2 queries. Now, I say the small differences, although there are 3 of them, are too small, while the 2 differences the other way are very significant. So in order to sum this up, so what I'm saying is, suppose my system produces values A, performance, let's say metric 1, metric 2, metric 3, metric 4, metric 5, that's system A. And system B produces the values M1 plus 0.01, M2 plus 0.02, M3 plus 0.03. So it's better than this, because these are the metrics, this is like average precision here. But on these ones, loses by a lot. So now, if I take the differences, I get minus 0.01, minus 0.02, minus 0.03. And in here I get 0.3, 0.4. These are sorted by absolute values already. So if I do the signed ranks, this is -1, -2, -3.
Oh, 4. That's fine.
So this system, which system will appear better if I sum this up? This is what?
The 8.
3 plus how much? Plus 3. So which system is better? A is better because it's a plus sign. A is better, but A lost on 3 queries and won on 2 queries. Right? This is the values average precision for system A, and this is the average precision for system B. B beat by 3 small score, but lost by 2 big scores. If I sorted the way I think it should be sorted with absolute small values at the top, the system A, it's better even though it lost on 3 queries. The winners are who? This is the winner on these 3 queries, and this is the winner on those 2 queries. So A appears better even though it lost on 3 queries because the differences were bigger. Who's with me? Do you have any questions about this? So now of course, this is a particular heuristic that you can say, okay, how much more queries do I need with small differences versus big differences to get the value? But I think everybody can see, if this is close to 0, I'm declaring null hypothesis maybe stands. But if this goes very highly negative or very highly positive, I can become clear at some point, sure, that one of the systems is better. Because again, bigger means, even though I lost on many queries, maybe those losses were small. I win big on few queries, and that's maybe enough. The big wins, the big differences will come at the bottom of the rings, of the signed ranks, and the bottom will add up bigger values or subtract bigger values at the top, which corresponds to the small differences. So these people like in IR this kind of test because it's more intuitive. It's a difference in these ranks is more intuitive than the p-values.
So it seems like there's a few assumptions that go behind the test. And so is there a way that I could easily tell if something's going wrong, if those assumptions are violated, that type of thing?
I think that's, you mean particularly about this test?
Yeah, like if you, let's say you don't have a normal distribution, for example, so that kind of thing.
As far as I know, this is more tolerant to the assumptions than the t-test. I may be wrong about that. I have to go check. But I think in here, what is the assumptions that are being made? I don't think it is, the only assumption comes into how do you interpret the score, right? What kind of thresholding for the score you need to have to say I'm sure something happened. The other thing that people have looked at in here that maybe it's part of the assumptions, it's how sensitive the metrics are. The deltas between metrics for some of these say average precision might be far more sensitive than other metrics, right? So these deltas here, let me see how do I put this. At what point there's a significant difference in the RAS? So I'm counting this thing as 1, this thing as a 2, as a 3, and I'm splitting. If I see the same value, I'm splitting the ranks between them. The point is, the 6 or 7 or 8 value will count as an 8, which is so much bigger than a 1. But what if the 8 value is actually pretty close to the first one? Like what if all the differences are very small? Is that what you?
Yeah, it's just, I mean, there's some moving parts, so I figured some things could break and wanted to make
So
sure.
I think his question relates to the following phenomena. More generally, when those tests fail, how can you screw up this test? Right, that's what he's asking. This is a very good exercise to do for a lot of algorithms and math, when somebody proposes some sort of mechanism, immediately think, okay, how can I make it, how can I break that thing? A lot of ideas are tested this way. So in here, I'm proposing this mechanism for testing if system A is better than system B. What would be a way to say, okay, I'm gonna make your test fail? So what kind of input values do I need? What happens if I have differences at 0.001? This is the deltas, A minus B. 0.002, 0.003, 0.004, 0.005, 0.006. This will result in what rankings? This is a +1, +2, +3, +4, +5, +6, +7. That's a huge win for the system A, right? You can say, okay, A won, but the actual differences were pretty small. Remember your average precision numbers? Average precision were like 0.2, 0.3, something like that. So 0.201 versus 0.200 is not a big difference in average precision, right? So here's this example where this is a massive win. This is, how much do I have here? 10, 28. Versus, how about I get the differences? Suppose the systems are close to each other, they get the same values but with some pluses and some minuses. So 0.01, 0.001, 0.002, 0.003, but this is a negative, 0.004, 0.005, that's another negative, 0.006, that's another negative, 0.006. Let's say I get something like this. What will this correspond? +1, -2, +3, -4, +5, -6, +7. What is this? -1, -1, -1, +4. So I think his question is primarily beating at the fact, hey, if I think we can all see here that if two systems A or B are significantly different, then this test will pop up the result. No, correct. So what does it mean for two systems to be significantly different? If system A is better than system B, it has to score significantly better on some queries at least. And maybe the other queries are small differences. When they're not significantly better, the system A or loses, it can't lose by a lot. We say if system A is better than system B, it means maybe sometimes they're like almost the same, or even A loses, but on some queries A has to do significantly better. The significantly better will come at the bottom, right? Because the significant better will be represented by bigger absolute values. So we'll have maybe the top, the small differences, those are the queries for each A and B kind of did the same, one beat the other, or small differences. And at the bottom we'll have the big differences where A consistently won. So in here, if the two systems, I think what I'm saying is the two systems are, A is much better, A is going to win the Wilcoxon test. The question is the other way. Can I declare A a winner when it's actually not a winner? That's a failure mode here. Look what happened here, right? If A has slightly better values for most of the queries, and I run this test, I'm going to believe A is a much better system, right? But in fact, it was not. All differences are just slightly better. This is a problem with Wilcoxon test. In particular, when you make some small change to your code, say you implement a small parameter change or something like that, all average precision jump a little bit, and you think it's much better. Now, statistically speaking, if I see these differences, is A not significantly better? Is A better for sure? Can I say, so what I pointed out is that A is not a much better system than B. The test doesn't say A is so much better, but are we sure A is better if we see these differences? Yeah, we getting sure. The problem, this is a problem between the t-test and this test. This test does not account for the actual values, just their ranked order, right? I could get the same exact test with any positive values. So it doesn't account for the difference in average precision and magnitude, just the order of them. The t-test will calibrate, will appropriately take into account the differences, right? Because it always does this, what is it? Deltas minus mu divided by the standard deviation over the square root of n. In here, small differences will be the same like big differences. There are many, many tests. I'm not sure I answered the question.
Yeah, it was just generally,
Yeah, I think the t-test can be violated more easily than this. Some examples here. I'm gonna skip some. User studies. So here's another. So people have been concerned about this, but for rather practical reasons. The statistics had this test many years before I had using them. The significance testing in statistics is an old story. In here, the real pressure came from the industry. The industry looked at academia numbers, and those also academic papers that report, my precision is better than his precision, and so on and so forth. And people in the industry were like, are we really believing this? Like, are we really willing to make a change in our production system just because a guy got 0.01 improvement? That's where the significant tests start coming into play. So another experiment that people did, they say 2 rank lists, right? And say, so how do we interleave results? We shuffle them, right? In a way that, what's the rule of shuffling here? I think the rule is we keep the relative order for A and B, right? You see B is dot 1, dot 2, dot 3, dot 4, dot 5, and A is 1, 2, 3, 4, 5, so it's kind of reasonably interleaved. We show this list to users, and we see what they click more on. Presumably a list like that, it's equally between system A and system B. So if people click more on this document, top of the B list, we're gonna conclude, hey, that's better than the top of the A list, because there are more clicks on the second one. That's the trick part.
What was the Wizard of Oz studies? There was a slide that said Wizard of Oz studies, like 3 slides ago or something. One more forward. It was like there were 3 bullets. It was the last
I see.
bullet.
Here?
Last but one. No,
Next one maybe?
next one.
Next one.
Yeah.
Oh, okay.
So let's see what this means. How do we, a lot of this comes down to how users perceive a metric. Like we say average precision is that versus that. Do users really are more happy with the system that has a higher average precision? So then we run these user studies, right? This is purely a simulation setup, right? The hardest part on these studies is that they're much harder for information retrieval than say for, I don't know, gym exercises or playing games or something like this. Because we give, like in the AP89 collection, we give users the queries, and it's different when you look for something you look for. You have that query versus when somebody tells you, think about relevance for World War II documents, right? I mean, World War II is a big topic, but imagine a person that's not familiar with World War II. It's not a natural user query for some people to ask a query that I just, somebody else made up with. So a lot of laboratory studies uses data and user queries that were created by some academics. They may not be relevant for the people who actually judge them. In a naturalistic study, it's better to observe the users doing their own thing. So what queries being used, what documents have been clicked. This is more like what they would do on a day-by-day basis. But it's much harder to evaluate, because now how do I know what results are good or bad? I didn't start with the test collection created like the trick people did. And the Wizard of Odds, I think it's something that takes a system, right? And then knowing the ground truth, I play with re-ranking of documents just to observe, how many people, if I do local re-ranking, will click on a different document, or experiments like that. Then there is information we capture, and this is a basic stuff. By now, user study capture people's attention. They try to capture their eyes. So there's user study that have cameras, and they detect not just where you click, but rather what parts of the documents are you reading, where you move the mouse, whether you say open a browser or something else like this, right? So in terms of capturing what happened, it's what you can write down that actually happened, and capturing complete user interaction of the person. It's still mostly done in the laboratory, so it's not like, okay, if you're free at home to look into a browser, you can pick up the phone and call somebody. In a user study setup, that doesn't happen. But there's a capturing of what parts of documents seem to be more relevant. And there are some studies that even have some brain machines that correlate what you do with your eyes and your ears with what parts of your brain get excited by that. The fMRI studies, so to see exactly what piece of information, how your body reacts to a certain piece of information. Right. So this is all kinds of experiments that are comparing what we can measure with our queries and our documents and our metrics versus our user satisfaction, how people react to those things. I think it has been shown overall that that metrics are indeed telling us the differences between systems if they're big. So the overall observation from a few years ago when I was involved with Trek and doing their evaluation runs for some tracks was that if you see a good difference between average precision values, like a 0.2 versus 0.3, that means that will be a difference for the users too. But below those values, even though statistically they appear significant, or by Wilcoxon test, something like that, it's not perceived as significant by the users. The main reason being, people don't read documents or click documents in the way the measures work. Average precisions or rank bias precision or those discontinuations model, they assume that people will read the documents one by one until they find the information and then stop. In reality, people don't read one by one the documents on the first page. If the result is there, we're educated enough to click directly on that result. And we don't have to click on the next one right away. And we take into account all kinds of other factors, right? We prefer Wikipedia documents, for example, so we're gonna go to a Wikipedia page rather than some other page simply because we prefer that domain, right? or who knows what else. So metrics cannot capture the actual user satisfaction because there's so many other factors that come into play. There's some very good studies about this. At some point in academic careers, people get all the promotions that they could get. Professors, for example, right? They get awards, they get promoted, they are associated professors, and they become, full professors, and they become, even have the chair, they have an endowment, and they paid off. And at that point in life, when people reach that point, some people decide to not be very active because they kind of have a full career, and they just advise students. But some people take that chance to say, okay, since I got all the promotions I could possibly get, this is the time to actually solve interesting problems that would not be publishable in academia. And I shouldn't say this, but it's true. And the best work can come out of people who really have no pressure on them to publish and to raise funds and all that. Simply because they don't have that pressure, so they could take on interesting problems. There's at least few classical examples of this, that people who retired, they got well promoted, and they retired, they stopped answering emails because they thought they have something better to do with their time. So I think some of there's some study that says how many of these research papers are inconclusive or wrong results. This is one of these people who decided to look at academic papers, performance papers for information retrieval, and say, we think a lot of them are actually not significant results, and here's the reason why. And this kind of paper, people don't want to publish early in their careers, They want to get, before you're trashing everybody else, you want to be, sure that you have things set up. I have other things that we can do. I forgot one, very important, this validity. I don't know what validity means in here, but what I mean by that, people would prefer documents that are simple to read. Nobody would click on a document that looks complicated, even though that might have a better information for what we want to answer. People would always like simpler things to read. Bullets, tables, Wikipedia documents, so on and so forth. There is a difficulty with websites that are complicated because the information is hard to find on the website, even though nominally speaking that page is relevant, as in it has the right information. How much do I try to track it down and find it? Did you ever put a query and you know what you want back is a table or a list of things, and you see a document that's blah, 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 and the list might be in the text, but you simply move on to another document, not because that document is not relevant, but just because it's hard to process the list out of a text as opposed to just a table with a list in it. So let me talk a little bit more before we take a break about other things related to this. Here's some people thought about. This stuff can get much more complicated than the basic. So it's a tutorial into evaluation metrics from a researcher from Japan. I think I mentioned this before. He's very famous for organizing things and tutorials and explaining how stuff works. So the significant testing, some of these tests are concerned with the sample sizes. So in Bootstrap is a technique to do sampling with repetition, which means out of few results, I give appearances of more results. And here's how to bootstrap test for two systems. You have a system A and B. There's again some mathematics of how to do that. The difference is we want to sample with replacement to correct for the sample size for the number of results that we get. The one that I want to, this is too complicated. The one that, this is the kind of researcher that got all the promotions. So he can ask at the end questions like this. Is everybody doing this? Is actually a useless with useless path, because what people in industry notice, there's way too many factors contributing to user, say, call it satisfaction, how happy I'm with the list of results, just the precision recall or NDCG. So there's the question of where is this user, what's the context, is it a sequence of queries or just one query? Is it something that he needs right away, I'm on the street and I'm looking for a location, or is something that is just reading for some, a long-term purpose? Is it on a mobile phone or a regular display? So I think in industry, there's a feeling that precision recall alone are not gonna get more advertisement money. Even if Google increases their recall or their precision, it's not gonna be something immediately beneficial. But there was something in here that I wanted to say. Student speed test. That's not what I'm looking for. This. Something important about all metrics, not just information retrieval, it's how much discriminative power they have. So that of course is a bunch of statistics behind that. You can see here I have a bunch of metrics, not average precision, but I have things like some version of NDCG and intent aware and expected reciprocal rank. Those are metrics. And discriminative power has to do with how much after a bunch of queries I can distinguish systems. So you can it's almost like being sensitive, right? So what's the sensitiveness of average precision versus NDCG? So metrics react differently to differences in the rankings, right? So what I'm saying is, suppose I get two systems. I don't look at the performance values, I look at the actual rankings. So system A versus system B. This is document 1, document 2, so on and so forth. This is document 7, document 1, document 2, so on and so forth. So how can I discriminate between those rankings? The system gives me a ranking of documents, B gives me a different ranking of documents. Suppose I have only local re-ranking. Is average precision going to be that different? Suppose I have one document move, but the rest of them stay. Is average precision going to be that different? So that's where discriminative power comes into play. How easy I can discriminate that some change actually happened. Not in the performance metrics. The test that we did, we took performance values for the t-test, and we have performance values for A, all those numbers here, performance values for B. This is addressing the problem of what metric do you want to use? Do you want to use average precision, or NDCG, or DQ, or whatever else is there? So people have looked at this. And then there were certain campaigns between Bing and Google. Researchers at these companies organized some experiments to compare Bing and Google directly. And then there were user tests specifically designed to run queries on Bing and Google, see the results, and see what people think about. Including the test with interleaving, so people don't know what they're clicking on. Concerning evaluation, one more thing that's related to machine learning is depending on how I set up the relevant assessments, I will never be able to judge all documents. What you guys doing now, you're judging only 600 documents out of so many. So what happens, I have to be aware of what documents I judge. In other words, if I have a bunch of documents and systems that are similar on the same topic and I judge that topic, I'll have more relevance assessments for those topics that I judged, and therefore I may create a biased advantage for systems that return that are more designed for this kind of topics, versus some other system who is designed for a different kind of topic. I will have evaluations that are not for that topic. So, like in the cross-validation in machine learning, in here, it's saying if this is all on one topic, the way we can imagine evaluating this A team or system is to say, I'm gonna look for the judgment, it's called pooling. Take the documents, the top 200 documents for the B, C, and D, and not take the ones from A, and then evaluate only using the judgments that I have for B, C, and D, the evaluation judgments. So I was suggesting this in class at some point, and I think I talked to some of you at office hours, and I think I mentioned it on Piazza. What you could do to test this kind of mechanism is to put a query that is related to your topic, but not one of the queries listed in Dropbox, which is used for the crawl. That will be a way to say, my topic is on the same, my query is in the same topic, but it's not used for a crawl document. So I have to rely on my crawler that will get documents from the other subtopics to get relevance documents on this one. So people have inherited biases in the way they do crawling and the way they do topics, and systems that come from the same teams that produce the system for evaluations are naturally get an advantage that way. So this is a known thing at Trek. Every once in a while, somebody has a good system that's poorly evaluated because their documents that they have in the system were actually not judged. I also have two papers here, but I don't think we're gonna have time for those. Let me see. I'm just gonna show you the papers. So one paper here says, how do we look at users versus evaluation metrics? So they talk about these metrics a little bit. The idea in this paper is to say, well, for most metrics, there is a weight on the ranks, this W. So if you look at average precision, NDCG, and many other metrics, there's a natural weight on the ranks. Rank 1, of course, matters more than rank 2 than rank 3. And then they define this C, which is, they say, this is roughly the probability to continue to the next rank implicit by the metric. And they look at this C, and they look at different metrics for how this C, the relative importance of the C as you go from rank 1 to 100, how this evolves. So that appreciates different metrics by how much they distribute the importance over the ranks. If it's a high precision metric, we'll put the weight at the high top ranks and nothing else. If it's more balanced metrics, you'll see a balanced plot. They also talk about users' models. But I think it's interesting to read this paper, if you do that, to start with the conclusion. In particular, things like that. What users actually do. Why do we need user studies? Because there's a lot of those metrics do not model the behavior of the users. They could jump around, they could stop, they could find the related information, and they decide to give up, so on and so forth. So here's some example queries that have been tried here to see what users react on. Deepest ocean point, wolf parade, Australian football rules, damaged soil fertility, extreme sports, theft and credit cards. This is the context of those queries. show you one more. We did this one. There's two more. One talks about, this is the guy who invented NDCG, Kalevo Jarvelin. And he's talking about here why higher evaluation is so difficult without direct input from the users. Like, of course, if you are a big company, you get direct feedback by clicks and other methods. But if you are in academia and you use test collections like AP89, why is this so hard? So that's all a little bit of introduction. Human performance reflects to even the judges could be wrong. So if we use a lot of evaluations like in homework 1 based on what judges did, the Curel files, how often those judges were wrong. That AP89, they were almost never wrong, but in a lot of other collections, the judgments themselves are wrong. So the question is, how do you adapt a metric to take into account noise in the judgments? If I tell you, average precision works on relevant judgments, right? But if I tell you there is a good chance, a 20% chance that these judgments are wrong, then can I still trust average precision to give me a good performance value? So the main factor I think they consider here is sessions, the fact that for queries that are simple, they could be measured immediately with simple metrics because people are looking for a location or a name or a phone number. But queries that are difficult, naturally a user will put several queries one after the other. So you have to judge the session performance somehow, not an individual query. And the last query that presumably gives the right answer because the user stopped, you can't judge only that query because it took maybe 6 queries to get there. So from a commercial standpoint, you want to judge the session somehow, not either the first query or the last query. I think that's this one. And many other, I have one here, again, type of studies. I think this person, Diane Kelly, she's only doing user studies for information retrieval. That's her career. That's what she does. It's famous for how to set up user studies, how to measure noise, how to differentiate users being experts versus users being students, which are students use a lot for user studies because they're part of research group, versus being crowdsourcing like Mechanical Turks that are paid very little money to do the job. How to differentiate that, how to set up those studies, how to measure the outcome of the studies, what do we collect and how do we report this, how do we train people to do a study. Before people take those studies, they need to have a training sessions to understand exactly what the job is. Let's see. I mentioned eye tracking before and brain scans that are not just answering questions and make you click, but they look where your eyes goes. They look how your brain reacts to sound and images. How to measure differences between different groups. There's native English speakers, for example, in IR versus non-native English speakers. There's male versus female. There's people educated, people not educated. And then what kind of queries, what kind of tasks we give to those people. There's some very simple tasks. Is the tiger in this picture or not? Versus very complex ones, philosophical queries and special knowledge queries like domain-specific queries. Right. So we don't only measure, I keep talking about satisfaction, but the truth is, it's not just whether I get the information I want or not as a user. The truth is, we also want to measure how efficient system was, like how long did it take to get that answer. document relevance don't measure things appropriately because we have a judgment per document, say this document is relevant, aka the information is in there, but maybe a very long document, very hard to read. And then there is the tiredness factor. Yes, I got to those documents, but this system, even if it takes shorter, people may feel more tired depending on the presentation of the results. So as you can tell from this, I think this is the last slide? No. There is a lot of effort put into those user studies. So I wouldn't think it's a bad idea to try to, actually we had a student, a master student, who now works at Amazon, I think, for quality assurance. There is a lot to do in terms of how to decide, how to measure user satisfaction with products, queries, results, so on and so forth. This is not a small niche career. If you're not decided what exactly you want to do, understanding how people react in front of the computer, whether they buy stuff or whether they query things or they look at friends' pictures, it's a big deal. And all the money is in there, by the way. The reason people get ads and click on ads has a lot to do with how they feel in front of the computer. You know, how happy are they to use Google or to go to Facebook or to buy things from Amazon. Okay, I think there's enough for now. I'm gonna stop here, take a small break, and then talk about something else. It feels weird. The projector, when I stay here, it doesn't feel like usual. There's the lights off, maybe. Maybe that's why. Oh. It's kind of hot today outside, no? It's more hot than usual? It felt, I stayed a little bit outside, it felt like way hot.
Probably because you're wearing black. Black is always heat.
But I felt much more warm than yesterday or the day before.
I prefer the winters now.
You prefer winter?
Yeah.
Aren't you from India?
Yeah, but this hotness is too hot, right?
Where are you in India from?
Bangalore,
And where is that?
South India.
So you should be used to hot.
But it's not so humid. So you can still, like we have still 35,
You're not
40, but
close
you
to
can-
the ocean?
No.
Ah, I see. Yeah, my country where I'm from, is dry. It could get hot up to 35, 38 degrees, but it's not humid. We have only a small sea, we don't have an ocean, but in India,
Yeah, but where I stay is
it's not close
not
to the
close,
ocean.
at least 160, 180 miles.
Hot today. Okay. What I want to talk a little bit is about machine learning for information retrieval for text. And I'm going to assume we've seen some basics of machine learning, like what it is and how it works and things like that. But we'll talk about algorithms. So, how do I do machine learning for text? So I need first to set a purpose. Machine learning for text, they say supervise. Set a purpose. For example, classification. And I need a train set that are documents plus labels. Classification with labels is a set, say, you know, options Y1, Y2, Y3 to YL. This could be things like sports, politics, economics, something like that. And then I need a train set. The framework of machine learning is I start with my index or some raw data, raw text. And then I generate a feature matrix. This would be feature 1, feature 2, up to feature D, and this would be document 1, document 2, up to document N. These rows are documents or observations or objects. The columns are attributes or features. Then I do training algorithm that produces a model. Learn model. And then I run testing or production. In testing, I know the answers. So I'm testing my model to see what it does. In production, when I'm using it to classify things, I'm using it because I don't know the answer. I'm predicting whether it's going to rain tomorrow or not. Of course, tomorrow I don't know if I'm wrong or right, but the reason is to tell people what to expect, right? Same thing for patients. I have patients in a hospital. I run a classification algorithm to see whether they are sick or in danger or something like this. Now, of course, at some point I'm going to know if I was right or wrong, but that's not the point of the classification. The point is to make a prediction that will help a doctor or a lawyer or you know, somebody who's driving to work the next day. So I do this, and I could have evaluation. Performance. I'm sure we all imagine machine learning working this way even before me saying it, right? The only thing that's not part of the standard machine learning here is that I have to get from text to a feature matrix before I can run the standard machine learning pipeline. Training algorithms we've seen, I think, before. Linear regression, for example, decision trees or supervector machines or deep neural networks, right? And then testing is running the learned model on new points, right? New objects, the ones that were not used for training, and see how well we do. Testing can be, just a quick comment here, could be much more complicated than you think. So computationally intensive, I mean, some methods for doing classification, once they train, which you consider an offline step, you can say, okay, training is done overnight or you know, one, it's not a query runtime kind of operation, right? It's done in the back end. Testing could be significantly expensive. So of course a decision tree or a regression model would be very fast to do testing. But there are some other models for which testing is very complicated. So the speed up, the computational aspect of how to do this in real time, it's a challenge. And in text, sometimes that happens. Things like CRF models, random fields, conditional random fields or something. Involves dynamic programming for testing efficiently, and it's hard to do that at runtime. It takes time. Anyway, our first, especially if we didn't see machine learning before, there's something very important about this feature matrix. That is, features or attributes have to be consistent. So it seems obvious when somebody says it, but it's not necessarily obvious if you did it in machine learning. That is, whatever this value here represents for this document 1 has to have the same, this has to have the same meaning for document 2. And these have to have the same meaning for document 3, and so on and so forth. That makes a lot of sense, right? I mean, you probably wonder why is he even bothered saying this. Well, what does the same meaning means? So these values, I'm picking feature 1 here, and I'm saying the relationship, whatever values here, these are all numbers, right? Whatever the number mean has to have the same meaning on every row. Think about regression, how regression looks like. So I'm jumping to an algorithm, say regression. Regression, say an h function, h of some document, d, is gonna give a score, right? The score is a sum for, say, t equal 1 to d of regression coefficients, let's say that's wt, times the feature value. Let's say the feature value here is d3, 1. So this is dt. So what does it mean in regression? The score that I'm getting, I'm assuming I trained the regressor already. I have the w's. These are the regression coefficients. These are the feature values. Consistency, it's not just an English definition. Like you could say, feature 1 is the word Virgil. And then in each document, these values in here are the counts, TF counts of Virgil in those documents, right? Like this is how many times the word appeared in the document. That's fine. But in terms of how this score, what this score means, is that really consistent? Is it the meaning of those feature values column, or I pick one column, is it really consistent in terms of what do I want to do with the scores? You can imagine I have here also labels, right? It's part of the same table, and this is y1, y2, up to 1n. So the relationship of what this means in a document has to have, if you want, the same kind of consistent impact to what the label is. So it doesn't work to have a feature matrix that's inconsistent in the following way. what this means for this document with respect to this label has to be what this means for this document with respect to the feature value is D31 here. Is D32, D3D. So one example where this doesn't happen, if you jump across queries. That's the standard problem in IR. If these are relevance for different queries, not the same query, then the word Virgil might be important for some queries and not important for a different query. And then if I train a model across queries, whatever I learn here, that it has to have a coefficient with respect to that query and this feature, it won't apply to the other documents. Again, it sounds obvious when somebody says it, but not uncommon to get it wrong if we haven't done machine learning before. So in IR, that this principle causes to be two kinds of machine learning classification. There's one that's per query. So the training and testing happens all for one query. For one query, I don't have the consistency problem. If Virgil is either important term or not, and then regression is going to learn the weight, and that weight would consistently apply for other documents because what I learned for Virgil being an important word or not being an important word will apply just the same. But if I want to train across queries, which is how we actually want to run information retrieval, we would like to have 25 queries for training and few queries for testing. Then I cannot use unigrams, because if I learn that some word is important for a label relevance for a query, it may not happen for the next query. For a different query, I'll have other words, which I didn't have in a training set for the queries, so that's not going to work. Is there any features that I can use across queries? What can I put here that will work across queries? So suppose I take the 25 queries from homework 1, and I say, you run a machine learning system like regression on 20 queries and test on the other 5. So I create two data sets, training versus testing. Training consists of documents, right? These are documents that we have in the curl file for queries, 20 queries, and those are the relevance of those documents for that query. You can imagine this in here is query 1, this is query 2, query 3, query 4, and query 5, right? So there's all the curl documents. And here would be the labels, the relevance judgments for those queries, right? Some document might be repeated if it's part of the first query and part of the second query or something, but that's very rare. My question is, what can I put as feature values?
The score.
Hmm?
The score.
What score?
Oh, from the BM25 or something.
Right. Is that a consistent feature if I put the BM25 score? Is the BM25 score in relation to this document and the relevant judgment for query 1? Is it consistent with the BM25 score for this document and the relevant judgments for query 4 or 5? Right? So then I can't put unigrams because unigrams don't give me this consistency. But I can put the BM25 scores if you think that BM25 score is a consistent column. But then I don't have that many things to put in, right? If I put unigrams, I easily get 20,000 features. But if I put scores, how many scores can you put? Right? We're talking about like 20 scores, 50 scores. So if I do it across queries, it's a very different business than if I do it per query. Per queries, I should also expect much higher results, right? Once I know what documents, few documents, it's like relevance feedback, right? Once I know what documents are relevant for that query, even if it's just 10, 20 documents, I'll be in a much better position to learn exactly what words to look for in the document for classification purposes. So I'd imagine that per query, I can get an average precision like 0.6. Once I give, suppose I pick a few documents, label them, and just run machine learning for that query, train a model for query 93, and then test it on some other documents for that topic, I'll get the high precision. But the cross queries, of course, I won't learn that much because my handles, my features are maybe those scores. Maybe I can put page rank values, that's all would be consistent. There's quite a few features that I can put, but I cannot get to 20,000 features. Okay. Okay, so the difference for us versus the standard machine learning would be creating this matrix. After that, we run the training algorithm. You guys are not going to implement machine learning in this class, so you can run a package like TensorFlow or linear or whatever you like. You're going to produce some scores, and we're going to have to evaluate. That's another a little trick in here, right? For information retrieval, it doesn't make sense to run like average precision, standard machine learning metrics, like things like accuracy, or things like, I don't know, directly F1. So if I get some results from machine learning, I have to ask, okay, how do I perform evaluation? I may have to rank some things based on the score produced with machine learning algorithm, and then use a ranking metric like average precision. So what I'm saying, again, is that in machine learning, we typically measure accuracy or F1 values or something like that. In here, we probably don't want to do that. We probably, depending how we set up the machine learning, we may want to do a ranking function, especially for relevance. Relevance is a very biased characteristic, right? So out of, I don't know, 10,000 documents, you can expect very few to be relevant. So you don't want to measure accuracy that's going to be very high if you just say non-relevant to everything. But if you measure a ranking performance like average precision or NDCG, we get that. So there is a problem here with the feature matrix that has to be created from text, and the problem here with the evaluation. As far as we're concerned for homework 6, we're not worried about the learning algorithms. But is regression supposed to be good for text? How many people have done machine learning? Okay, like a course or like a personal a course? Is regression good for text?
I think the neural network is better. Neural network is better if you consider the context, but here it doesn't consider the context.
Context means the order?
Yeah,
of
the order
words?
of the words.
Okay. Right. This is a bag of words representation. So every word corresponds to a unigram. The order is lost. I get the count, but I don't know which word comes before that. Right? So to run something that takes into account order, anything, not just neural networks, I need to have the order somehow represented. If I don't have the order, it doesn't matter, right? So, but let's say we stick with unigrams for now. Is regression good or bad? Regression is train the best model that you can, the best linear model that you can. And for classification, we don't use regression, linear regression, we use logistic regression. We have to transform the scores into black or white, right? So we say logistic regression means linear regression transformed into, if the score is low, we call it 0 or black or low probability. If the score is high, we call it truth or relevant. And there is a logistic function that goes between scores and 0, 1. Fine. So is this good for text? What are the advantages of this mechanism for text? Or it's not good for text? So I'm asking this in a funny way, maybe, because if you say I took a machine learning course, you go to an interview, this might be the first question they ask you: is regression good for text or not? I know, because this is like such a simple question, and it will test immediately how much experience you have with machine learning and with what kind of data you play with.
don't you need to pull like a feature out of it to be meaningful for regression? So maybe if you pulled out like sentiment or like, you know, some of these other things, and then put that in a regression.
So you mean other features than the unigrams?
Yeah, I mean the unigrams don't make a lot of sense to me. Just looking at it that way, like I don't really know what you would do with that. I mean, if it's a higher
Most of
level-
machine learning is run by unigrams. Most of classification of documents is based on unigrams and bigrams.
Yeah, but you said how to put it in regression. I wouldn't do that in regression, or I haven't. So, you want to do something else? We can talk about it. But
So suppose I have unigrams and bigrams. I don't have other things, tags and sentiments and order of text. Is regression a good thing or not? Okay, so what are the advantages? So let's compare with a different algorithm, make it easier. I'm going to say a decision tree. Right? These are the two typical algorithms that you study day one in machine learning, regression and decision trees. Right? Decision trees are effectively a systematic way to ask things like, if you see that word at least that many times, increase the score by something. If you don't see that word, decrease the score by something. And you have a collection of these rules, which in a decision tree are not so many. You can expect things like 20 rules or so. And you apply those rules and you get minus, plus, minus, plus until you get some sort of score, right? In regression, you get a linear combination of the feature matrix, the features, the columns for each thing, and you get the score. But in here, the immediate advantage compared to a decision tree is that you have a lot more terms. Regression can associate a weight with every single one of the unigrams. So if I have 20,000 unigrams or bigrams, this is potentially 20,000 parameters. Decision trees, as a analogy, right? Decision trees, by comparison, most trees will never get to anywhere close to 20,000 parameters. Imagine if I run a decision tree, right? If it contains a certain word, do something. If not, do something else. Then do something, then do something else. Like this is the number of splits in the tree. Even though I can go deep, I will never, the thresholds are the 3 parameters, right? This will not have that many parameters. That is if my feature has 20,000 things in it. But if we're talking about across queries, right? Then across queries I use a few scores. That will not be so many. So linear regression has an advantage that it can use on a big matrix, very wide matrix. It has a lot of complexity due to having a lot of parameters. So the typical bag of words representation is between 10,000 and 100,000 unigrams and bigrams. And that gives regression an advantage in that it has high complexity. But that can be bad too. High complexity means it allows to overfit very easily on weird documents. Because I have a lot of ability to play with those weights to create any kind of model I want. So the regression on text has this advantage, it uses a lot of features, but I have to somehow control this complexity. So what can I do?
You can do regularization.
I can do regularization. Which kind?
L2 L1.
Which one does what? L1 controls how many coefficients you have, effectively. L2 controls the spread. If between having some large coefficients and small coefficients, or having balanced coefficients, L2 favors the balanced coefficients. So again, we don't need to understand exactly how regression works internally, but for a lot of text problems, regression can win simply by the number of coefficients you can use if you don't let it overfit. So you've probably seen something like this. When you study regressions, if you did, I'm not assuming that you did, so I'm going to walk you a little bit through how this works. But if you did machine learning, you've seen something like this. There is a linear score, and there is an objective. So we are setting X are the feature values here for each object. D is the 1, 2, 3, 4 dimensions. We want to find the W's that minimize a certain function, which you call error or objective of regression. This is the object, the objective that we are minimizing. So what is it saying? When I apply this function to an X, I get this linear sum. I want the result to be as close as possible to the label or the target. And sometimes that's a 0, 1. Sometimes it's a number. Like typically when I do linear regression without the logistic function, just linear regression, it's predicting a quantity. So like a house price or salary. That's why. And this is a very famous objective. It's the difference between what I predict and the truth squared. And it's summed over all the data points. This is the regression L2 norm least square loss. Right? How can I solve this? So now it comes down to pure mathematics of finding the W's that minimize this objective. You can, instead of reading HW of X, you can just read this sum. Right? It's a sum minus y squared. So what are the methods that will allow me to find the W's?
You minimize.
I minimize by numerical analysis, right? Like gradient descent, for example. So I can do that. In here, it turns out that for linear regression, there is a closed form solution. So we don't have to iteratively run gradient descent or Newton's methods or whatever optimization. I could just do this pure with linear algebra and with a trace function. And if I go through all the math, which I don't want to, I end up with more math. And eventually, I end up with this equation that says W vector of coefficients have to be X transpose X at minus 1, X transpose Y. Who's Y in here? The vector of labels. Who's X? The feature
The
matrix.
feature.
So that's a closed form for double. This is impossible to use in practice, by the way. Why?
The inverse of that matrix.
We cannot inverse that matrix, or very unlikely to be a success, that inversion. I mean, you can try for small matrices, but for big matrices, it's impossible. So even though there's a closed form, for logistic regression, we don't have a closed form. This is just for linear regression. But even for linear regression, it's impractical to solve it that way for big matrices, especially for text that has big number of dimensions. So how this stuff worked, I don't want to go through the math, but the principle was taking derivatives and set them equal to 0, right? And just solve the equation, where is that 0, where's the delta on each W, 0, and then satisfy the equation. This is the logistic transformation that maps scores into 0, 1. Right? You can make it arbitrarily sharp or loose, so we can make it much more sharp or more loose if we want to by just controlling a constant next to z there. And that's used for classification. Now, what do we have for homework 6? I don't think you can see this yet. So the first job you're going to have in this homework 6 is producing the feature matrix. Now, this is a problem to do in practice, and I can tell you, while Python, for example, scikit-learn will produce this for you. If you feed a bunch of text, it will generate the feature matrix. It's very inefficient. Let's go back to the IR and indexing and figure out how would we do this efficiently. What would it take to process a feature matrix? So one thing that I have to do is to figure out what are the columns. But suppose I do that. I have each column is a unigram or a bigram, and I know what it is. Then how do I get, say, the column, the whole column here? This is the inverted list, right? This is exactly, if I look at that term, obtain from the index the inverted list, which is that term, what documents it appears, and with what counts. And I want to store it in a sparse format, but should it be a sparse format by the column, like in the inverted list, or should it be a sparse column by the row, like in the document? By the row? But how my algorithm is going to use this matrix? So first of all, if I have a sparse matrix, can I implement regression with a sparse matrix? Can I look back at this regression equations and see if I can do them with a sparse matrix? Let me look at the gradient descent nodes, because that's the one that can't see much in here. So I have gradient descent. I'm sure you know how that works. Find the minimum of a function. And then I apply gradient descent to my regression function. I get these updates that are updating the W's, right? The more I run gradient descent, the more I update these W's regression coefficients. Can I do this if my feature matrix is stored in a sparse format?
I think if it is sparse, then you will get like, you will assume it's optimal earlier, and so because the difference is small. Because
So,
it's 0, 0.
I'm not ready to answer that question. I'm just saying, I think everybody here says, how hard can it be to run regression, right? Like, we're not going to implement it, we're going to run a package. But I have a few questions for you. Number one, how do we generate the matrix? I don't want you to call a package for the feature generation. So I want you to obtain the feature matrix by yourselves before you run regression on it. So you have to write that code or find a way to do it. It's not hard, but it's not easy. The best way to do it is from an index directly. If I have access to Elasticsearch index and I have all the documents in there, how do I generate a feature matrix? And the efficiency matters. We're not going to grade the efficiency, but this is a key for running machine learning on text. How fast do I generate the feature matrix? And some of the Python functionality for doing so doesn't work for large scale. So if I really have a lot of documents with a lot of bigrams, so I'm talking of a matrix that's 500,000 documents by 200,000 dimensional, can I write Python and obtain that feature matrix or not? So for the jobs we did, we had to implement that. We did it for Elasticsearch, but we had to go to the low-level Elasticsearch Lucene to obtain. I think the homework sys has a pointer to the code we had to obtain such a feature matrix. So that's option, that's the first part. Then secondly, I'm going to allow you to run regression, a library on that matrix, but you would have to explain to me if it's a sparse matrix, which probably is. I don't think any one of you can write down really a matrix that's 85,000 documents times 20,000 unigrams, so it's got to be sparse. Why liblinear works on sparse data? How does it do it? I'm going to talk a little bit more about this next time, but that's another question that you have to be ready to answer. We allow you to use packages, but if you're to implement regression yourself, how would you deal with the sparsity, most of the data being 0, and the sparsity storage, which is some values are not even there, right? Of course, that's how it works, and it will be easier, much easier to run on a sparse matrix than a full matrix. Okay, and I think homework 6. So this is what's written here is across queries. Remember when I said there's 2 types of machine learning? Per query, I have to deal with features that are unigrams, and so I have a lot of consistency if I'm in a query, but there's a lot of sparsity. For across queries, if I have 20 training queries and 5 testing queries, we'll talk about setup cross-validation next time. But in here, do I have a sparse feature matrix? So what are my feature values if this is across queries? You say BM25 scores, and I can add some other scores, right? How many of those scores would I have? 10, 20 scores. Is that a sparse matrix or a full matrix?
That's full matrix.
That's a full matrix. There are not that many zeros in here, right? These are all BM25 scores or language model scores. So in here, I don't have to worry about the sparsity aspect of things. Right? That's good. But there will be an exercise where it's for a query where the features are unigrams. Maybe that's spam classification, for example. Spam will determine that some unigrams are very important words for spam, right? Then how do I run machine learning, like regression, on a sparse matrix? The other thing that I want to mention today is as opposed to regression, I was mentioning that I can have a decision tree. So if you haven't done machine learning, again, we're not assuming for this class that you did machine learning before. There are 3 algorithms that you have to know before, like, the first batch when you learn machine learning. One is linear regression. Decision tree, and naive Bayes. So you're going to have to know how those 3 algorithms work. We're not grading anything in this course, how well do you understand those things, but I'm telling you as experience, you've done some machine learning and some of you plan to do a lot more machine learning, right? You have to know first these 3 algorithms to the detail of how they work. And my recommendation for anybody who want to be a data scientist, implement those 3 algorithms yourselves. I know it takes time, especially some of them are quite tricky to do with sparse matrices and so on and so forth, but you should implement those 3 algorithms before you study serious machine learning. Because machine learning, you can't study properly if you don't know those 3 things. Everything is based on them. Neural networks will be based on linear regressions a lot. Gradient boosting is based on trees. And all the generative methods are based on something like naive Bayes. So decision trees, how do they work? So how does linear regression find those coefficients? It does a global optimization. And the reason it can do it without closed form is that the objective that I showed you is sum of WT dt minus y, this is a sum over all the documents, d squared. This is a convex objective, so it has a global minimum. So then if I keep hammering at it, I'm going to get to the minimum. The gradient descent can be very slow, so there's better numerical methods than gradient descent to get to the minimum of that. But decision trees are trying to do something greedy instead. Decision trees look at the data, what's positive, what's negative, or what's economics versus what's sport, and say, give me the best feature that can differentiate them. Once I make that split, in here something with cars and some other data set. So once I make a decision, look at the feature, and I have several options for that feature, I'm sticking with that decision. That will never change because I already made it. So I'm going to the next decision. And in here, I only have to deal with the data that has been already split. So in terms of these alt features, if I'm in here, everybody will have the alt equal yes. So in here, I already know that the data I'm dealing with now, it's only that has been split that way. So I'm looking again, I'm asking the same question. What's the next best feature in order to split my data again? So decision trees can run deep, but even if I run it down to deep depth, 10, I'm not generating that many rules and features. Right? Assuming it's a binary tree, by depth 10, I have how many leaves? 2 or 10, right? 1,000. So there are not that many splits. Regression can use a lot more coefficients if we're allowed. Okay, so what is the advantage of a decision trees versus regression? What are the disadvantages? So we already said number of coefficients. Regression can use an enormous number of coefficients for text. Decision trees, unless you run it very deep, they were not going to use that many. What's another difference? This is greedy. This may not reach an optimal, globally optimal classification, no matter how hard you run it, because it doesn't optimize a global objective. It's a greedy method. Once he made a decision, he's going to stick with that decision, and he's going to split further, but not going to correct the first decision he made. Regression with gradient descent, or with any other method, can change those coefficients back and forth until they get to the global optimum. What else? Those chunks of the tree can become very small. After a few splits, some of the leaves can have very little data. So the decisions made on that small data are unreliable because it can cause overfitting. Since I'm making a decision with only 2 or 3 data points in there, I don't know how that decision is going to generalize for other documents. Anybody implemented the decision tree? I literally write the code for the decision tree. No? Okay. There is another difference. Decision trees can be very robust in terms of what classification they can produce. Think about this way. What can regression do for me? I'm having a space here. These are my 2 coordinates, x1 and x2, right? These are the input dimensions. And this is the y, this is the label. So what regression is going to do is going to correlate linearly. It's going to find w1 x1 plus w2 x2. It's going to find me 2 coefficients w1 and w2 such that this approximates as best as possible y. That's its job, to do this, to find me this w1 and w2. So then, if I found those w's, how this regression is going to look like in this picture here. Trying to draw it. Once I found the W's, so I trained it and I got the two coefficients. Maybe it has a 3 term too. I can have W0. That's times 1 bias, right? How's that going to look? This is a what?
Linear community.
Yeah, which is what geometrically, if I plot it, what is that?
Will like draw a line that is close to.
Right. So to try to find a line, and for each x1 and x2, it's gonna. How do I determine where x1 and x2 is on the line? So if I pick a certain point, so I have a point here that's the coordinate on the point, and this other coordinate, right? This is my input. This is my x1, x2. How do I get the value on the line?
The value on the line will be the minimum distance from the that point to the line.
Make a projection like this.
Yes.
Really? So I'd say I don't want to make this class about machine learning, but we need to maybe either the ones of you who study a machine learning course, you need to fresh up. The other ones, I would suggest because we don't want to do a class about this. I have my machine learning notes, very good notes by the way. They most of them from Stanford. So I would say you need to look at the regression and figure out how much of it is new for you and how much of it you already know. Right? This is a very basic treatment of regression. My point is, okay, this is actually a line, we're confused a little bit what the line means, but how decision tree look like? If x1 is bigger than something, do this, and if x2 is more than something, do that. If I plot geometrically a decision tree line, how would that look? It's going to be a line?
I mean, it does not have to be a straight line.
The decision tree?
Yeah.
Yeah, but what does it look like? It's not a curve, it's like a stair. Decision tree can look like this. All these are parallel with the axis. So every time a decision tree, the decision tree split, sometimes it says, is x1 value smaller than 2? Yes. Then ask, is x2 value bigger than 7? Yes, no. No. Is, maybe I'm asking here, is x1, so this is bigger than 2, is it smaller than 5? All this causes a separation for a segment that's perpendicular to some axis. Right? Every time I say this is the side that's smaller than 2, that's bigger than 2, what I'm putting a line on 2, and I'm saying there's two regions, one bigger, one smaller. So suppose I look at this plane, at this drawing differently now. I'm having x1 here, x2 here, and y sticking out the board to you. So I rotated this plane, y sticking out. Right? This is the same as that. I took the whole thing and I rotated such that x1, x2 is the plane board, but the y, it's an axis that comes this way. A decision tree, the deeper I run it, a simple decision tree, x1 smaller than 2, do something versus something else. It's here's the 2, right? It splits into two regions. That's the first split. It says on this side there's something going on this side there's something else going on. Right? That's the split right here. Now, in this region, it does what? Says is x2 bigger than 7. So where is 7? 7 is here, right? Here's another split. So now I have 3 regions. It's this side, and this side. And then it says, okay, this one here, I'm going to ask is x1 smaller than 0? So for all the x1s that were smaller than 2 and bigger than 7, I'm in this region now, I'm going to ask is x1 smaller than 0 or not? So this region, I'm splitting it again at 0. So now I got this region and this region. So in the end, I'm doing those little splits. I take every one of my regions and I split it in half, in two parts, right? Then I'm going to split here, I'm going to split here, then here, then here, then here, then here, and then I get all these regions. And in each region, I'm predicting the value. When I stop splitting, all this region that got unsplitted is going to be predict. This is, sports. My point is, these are very different things. Linear regression cannot map things this way. Linear regression is going to look like a line. It's going to be the best possible line, but not a zoo of splits. A decision tree can act like a line if it does a lot of splits that look almost like a line. See, like this one here? If the splits are very tight, eventually it starts looking like a line. But it's still a stair. It's a stair that approximates a line. The important part here is not the mathematics of machine learning, like how gradient descent works. That's for the machine learning class. The algorithms. How do you take an objective and implement it and take the inverse and make it work? For this class, what we need to see, if we deal with text, what's the right way to set up text and learning algorithms to use to obtain the results that we want? And we let the mathematicians figure out the math. Okay, if that's my goal, how do we actually run the internals to get the best W's? But our question is, what do we do with the best W's once we have them? So I'm going to stop here. I'm going to put homework 6 online, but I know it's not going to be. Probably need at least a week or so. Maybe by next week you get to it, hopefully. You think you can finish grading 600 documents this week? Yeah? And then there is a system to see grades that's not working yet. That's due to the CCIS playing with this summer they have an update on how to run the CGI scripts. So before I fix that, you can ask the TAs what your situation is. What I saw in the grade sheet is that most people who did the homeworks eventually got the full points. So that's as expected. If you want to see if you need some data on your grades before I make this system work, or you can check what you have, you can ask me directly or you can ask the TAs. They have the grade sheet, so they can tell you right away what grades you have. We won't have an exam, so it all depends on these homeworks, 6, 7, depending how much we go. I think there'll be one that combines 6 and 7 together. We may drop an exercise. It's not, as I said, uncommon in this class for most people to get an A, but it's also not uncommon for people to, struggle with getting everything done. The last day of the grades is when? 25th. That is a Saturday. So I know some of you ask about buying plane tickets and such, right? So you need to finish these homeworks. I'm going to post today, tomorrow, the last homework. And as soon as you have all the homework demos, you can leave. But I can't tell you what that date will be. That's up to you. If you want to leave earlier, you're risking by buying the plane ticket. Instead of it's 25 degrees that you buy it on the 18th, right? Because you think I'm going to be all done, and then you're not done, and you have this problem of you're already flying over the continent. So if you think you're done, you can decide your vacation plans and such. As soon as you have the demos, you can leave, but just make sure you can do it.